This would be section 4.3 on logarithmic functions. Alright. And logarithms. The horizontal line test shows that exponential functions are one-to-one and thus have inverse functions. The equation defining the inverse of a function is found by interchanging x and y in the equation that defines the function, starting with y equals a to the x power and interchanging x and y yields x equals a to the y power. So for that, a logarithm for all real numbers y and all positive numbers a and x, where a is not equal to 1, y equals log base a of x is equivalent to x equals a to the y power. The expression log base a of x represents the power to which the base a must be raised in order to obtain x. So let's put that definition of logarithms to use. If you look at example 1, writing equivalent logarithmic and exponential forms. The table shows several pairs of equivalent statements written in both logarithmic and exponential forms. What they want us to do is to complete the table. So if you look at log base 2 of 8 is equal to 3, the exponential form of that is 2. Exponential form of that is 2 to the third power is equal to 8. Okay? So you always take the base of the logarithm is the same as the base of your exponential expression. Alright? You go in this general direction. So 2 going to the third power is equal to 8. So if you look at this next one, you have log base 1/2 of 16 is equal to -4. Well, the exponential form of that is 1/2 to the -4 power is equal to 16. Okay? And the same holds true with the next one. If you have log base 10 of 100,000 equals 5, well, that's 10 to the 5th power is equal to 100,000. Alright? In the same manner, now we can change an exponential back into a logarithm form. So we have 3 to the -4 power equals 1/81. Okay? So the base of this exponential is 3. So the base of our logarithm would be 3. So we would write log base 3. Okay? So log base 3 of 1/81 is equal to -4. Let's try that again. Let's look at the next one. We have 5 to the first power is equal to 5. Well, if we have 5 to the first power is equal to 5, then the base of our exponential form here is 5. So the base of our logarithm would also be 5. So this would be log base 5 of 5 is equal to 1. Alright, and let's look at this last one. We have 3/4 to the 0 power is equal to 1. The base of that exponential form is 3/4, and so we would say log base 3/4 of 1 is equal to 0. Let's explore this some more. If we look at our next example, example 2, what they want us to do is to solve some logarithmic equations. to solve the logarithmic equations. One way that we can solve this logarithmic equation is by changing that logarithmic form to the exponential form. So if I have log base x of 8 over 27 equals 3, to change that back into an exponential, that would be x to the third power equals 8 over 27. Now it's a little bit easier for me to solve. If I have x to the third power equals 8 over 27, I would take the cube root of both sides. So I would say the cube root of x to the third power equals the cube root of 8 over 27. Now the cube root of x to the third power is just x. And then the cube root of 8 over 27, and you can break that up. You say the cube root of 8 is 2 over the cube root of 27, which is 3. So x will be equal to 2x. Alright, using that same conversion, converting from a logarithmic form to an exponential form, we can solve this next example also. So let's say we have log base 4 of x is equal to 5 over 2. Alright, when I change this logarithmic form to an exponential form, this would be 4 to the 5/2 power is equal to x. 4 to the 5/2 power is equal to x. Alright, and from here we can use our calculator. Alright, and we can put in 4 to the 5/2 power. Okay, you just hit 4, hit your rooftop symbol. Alright, right here, hit that rooftop symbol. Alright, left parentheses, and we say 5 divided by 2. Close your parentheses and hit enter, and I get 32. X is equal to 32. I'm going to take the positive side of that, which is the positive 32, because of where that x is coming from. Alright, it's coming from the index of that logarithm, and that can only be positive. Alright, if we look at C, I have log base 49 of the cube root of 7 is equal to x. Alright, so if I change this to an exponential form, this would be 49 to the x power is equal to the cube root of 7. So just like the previous section, what we will try to do is try to get our bases to be the same. So 49 and 7, I can change those that the bases are the same. 49 I can rewrite as 7 to the second power. That goes to the x power. And the cube root of 7 can be rewritten as an exponential as 7 to the 1/3 power. Remember, you can write any radical as an exponential as long as you put the power on top and the root as your denominator. A couple more steps. If we have 7 to the second power raised to the x power using your power rule of exponents, this would be 7 to the 2x equals 7 to the 1/3. And at this point, since our bases are the same, we can then set their exponents equal to each other. So this would be 2x equals 1 over 3. Divide both sides by 2. And I get x equals 1/3 divided by 2 would be 1 over 6. Time to reflect. Can you describe a process for solving logarithmic equations as shown in example 2? Basically, what we did there was we changed those logarithmic equations into exponential equations, made it a little bit easier for us to solve. Alright, the next thing we need to cover is properties of logarithms. Right? The properties of logarithms enable us to change the form of logarithmic statements so that products can be converted into sums, quotients can be converted into differences, and powers can be converted to products. So your properties of logarithms for x is greater than 0, y is greater than 0, a is greater than 0, and a is not equal to 1, and any real number r, the following properties hold. Product property, the log base a of x times y equals the log base a of x plus the log base a of y. So the logarithm of the product of two numbers is equal to the sum of the logarithms of the numbers. Quotient property, log base a of x divided by y, or x over y, is the same as log base a of x minus log base a of y. So the logarithm of the quotient of two numbers is equal to the difference between the logarithms of the numbers. Power property, log base a of x to the r power. Basically, that r comes down to the front of that log, so that's r log base a of x. So the logarithm of a number raised to a power is equal to the exponent multiplied by the logarithm of the number. Logarithm of 1, log base a of 1 is always equal to 0, and base a logarithm of a. So if your base of your logarithm and your index of your logarithm is the same, it's always equal to 1. So let's use some of these properties on our next page. For example 5, using the properties of logarithms, what they want us to do is to rewrite each expression, assume that all variables represent positive real numbers with a not equal to 1 and b not equal to 1. So for a, A, we have log base 6, and that should be 7 times 9. I can rewrite this as log base 6 of 7 plus log base 6 of 9. And that is using the product property for logarithm. For B, log base 9 of 15 over 7, I can rewrite this as log base 9 of 15 minus log base 9 of 7. And that is the quotient property of logarithm. For C, we have log base 5 with the square root of 8. Right, before I use power property here, I'm going to change that radical expression so that it has an exponent. It's an exponential expression. So log base 5 with the square root of 8 is the same as the log base 5 of 8 to the 1/2 power. So it's understood to be 8 to the first power on the inside of that radical, and the root of that radical is 2. So we can rewrite that as an exponential expression is 8 to the 1/2 power. Now, using the power property of logarithms, that 1/2 comes to the front of that log, so this would be 1/2 log base 5 of 8. Okay. So now for D, let's put a couple of different properties together into one. So look at D, you have log base A of M in Q over log over P to the second power, T to the fourth power. Alright, so basically, I'm going to write a logarithm for M, for N, for Q, for P to the second power, and T to the fourth power. So here we go. Up top, those will all be plus signs. At the bottom, they will be minus signs. So this would be log base A of M plus log base A of N plus log base A of Q minus, now P to the second power, that 2 comes to the front, so that's 2 log base A of P minus, because we're still at the bottom, T to the fourth power, so that 4 comes to the front, and this would be log base A of Q. Okay. If you look at E, log base A of the cube root of M to the second power. First, I mean to make that conversion on that radical expression, so this would be log base A of M to the 2/3 power. And so now that 2/3 comes down to the front because of the power property, so this would be 2/3 log base A of M. F, if we have log base B the nth root of x to the 3rd power, y to the 5th power, z to the m power. One thing I will do is I will make this conversion on each one of those terms on the inside of that radical. So I can rewrite this, each one of those as the exponential. So this would be log base B of x to the 3 over n, y to the 5 over n, over z to the m over n. Now, I can write out my logarithm as log base B. 3 to the n power goes to the front, and x is my index, plus, because I'm still at the top, 5 over n comes to the front, and that'll be log base B of y, minus, because I'm going to the bottom, to the denominator, m over n log base B of as we look at the last example for this section, example 6. Alright, we'll be using the properties of logarithms. Now, what they want us to do is to write each expression as a single logarithm with the coefficient 1. Assume all variables represent positive real numbers, with A not equal to 1 and B not equal to 1. So for A, if I have log base 3 of x plus 2 plus log base 3 of x minus log base 3 of 2, what they want us to do is to write this as one single log base 3. Now what I pay attention to is in the front of that log is understood to be positive. So when I see a minus log, then I know I'm going to have to write with a fraction bar. So up top, I'm going to have x plus 2. Alright, log base 3 of x. So that's times x. Alright, minus log base 3 of 2, so the 2. So I wrote this expression as 1 log. Let's look at b. I have 2 log base a of m minus 3 log base a of n. So I see now that I need to write this as 1 log base a. I see now that I'm going to have a fraction because I have a minus sign. Now, when there's a number in front of that log, remember, we write that back as 1 log. That's going to be the power. So 2 log base a of m would be m to the second power minus 3 log base a of n, so that would be n to the third power. Alright, and let's look at c. We have 1/2 log base b of m plus 3/2 log base b of 2n minus log base b of m squared n. All of those are log base b, so I'm going to write this under 1 log base b. Now that's 1/2 log base b of m plus 3/2 log base b of 2n minus log base b of m squared n. Since I see that minus, I know I'm going to have something at the top of my fraction bar, something at the bottom. First part, that's a positive 1/2 log base b of m, so that would be m to the 1/2 power up top plus 3/2 log base b of 2n, so that would be 2n to the 3/2 power up top minus log base b of m squared n, and so we would just put m squared n at the bottom. Seeing those fractional exponents there, we can make one more conversion, and we can say that this is log base b, m to the 1/2 power and 2n to the 3/2 power. I can put that all under one radical. And that would be a square root radical of m there is no property of logarithms to write a logarithm of a sum or difference. So now, you try exercises 3 through 9 odd, 13 through 17 odd, 63, 65, 69, 71, and 75 through 81 odd for extra practice. You can check the answer to these odd problems